Okay, I am Kikuuwe from Hiroshima University, Japan. Thank you for your introduction. Okay, the title is Nonsmooth Modeling of Hydraulic Systems and its application to control. Nonsmooth modeling, yes. The point is Nonsmooth modeling. And yes, I applied this to hydraulic systems, and also I applied that for control of hydraulic excavators. And this is a kind of overview of my research topics. And basically, I have been working on robotics and mainly the control of modeling of robotic systems. And many projects are related to differential inclusions, and including set valued functions and yes, what we call non-smooth systems. And well, yes, I have been working on robots, and it's driven by electromechanical, electromagnetic actuators. But recently, I started working on hydraulic systems, and I noticed that hydraulic systems can also be described as differential inclusions using set valued function. And I applied that way of thinking to the modeling and also the control of the systems. Okay, and today's topics, there are 3 topics, and it's a kind of very quick overview of 4 of my previous papers. And one is still under review, and one is modeling of hydraulic actuator. And yes, I say it's quasi-static modeling, and I modeled it as a non-smooth actuator. And I applied sliding mode position controller to such systems. And as you might know, the sliding mode controller, it's a non-smooth controller. And it can be said to be non-smooth controller applied to a non-smooth actuator. And I invented 2 ways to implement such controllers, such actuators. Okay. And the first one is about the modeling of hydraulic systems. The motivation came from collaboration with construction, the manufacturer of excavators. You might know this kind of excavators. It's a Kobe construction machinery. And they wanted me to figure out new techniques to deal with complicated dynamics of excavator systems, well, especially hydraulic systems. And they invited me to operate the excavator, and I found that the response of excavator it's very interesting, and I couldn't figure out what kind of transfer functions can describe the response. And so my question was my academic motivation is the question: what kind of equations can describe the response of hydraulic systems? Okay, this is it looks complicated, but this is a very typical hydraulic system, hydraulic circuit to drive one hydraulic actuator. This is the actuator itself, and there are 2 chambers here, and the oils should be injected into this chamber and this chamber to move this rod in this direction. And there is 1 pump, and there are main control valves, and which adjust the flow of oil. And there are many different components, but they are necessary to keep the safety. For example, these relief valves are necessary to relieve the oil, to relieve the pressure from this part when there is a large external force. And also this relief valve, it's also necessary to make the oil escape when these valves are closed. So although it looks very complicated, we can say that it's a almost minimum configuration of hydraulic system. And yes, and we assume that there are 4 control valves, and so 2 of them. One needs to adjust the flow. Oil flow from pump to this chamber, and this one is from pump to this chamber, and the other this chamber to the tank. And we assume that they do not act independently, and we assume that there is one control input U, which is from -1 to 1, and it is projected into these opening ratios. In this manner. Okay, and this is a kind of quick explanation of how it works, and it is non-smooth. And well, no smoothness happens, especially when all valves are closed. When all valves are closed, it doesn't move. But when there is an external force applied here, the oil must escape from these relief valves. And so it acts like that. It means that, well, the velocity, when velocity is zero, the force can be any value, well, between the relief level. And the external force exceeds this level, then the actuator starts to move like that. And the same thing happens in the opposite direction. So it exactly acts like a Coulomb function. And also when there is when these valves are open, well, it acts like a nonlinear viscosity with saturated force, and at the opening ratio U becomes large, it becomes less viscous. The viscosity takes place because of the resistance of these valves. Okay, and this is a very quick, well, kind of intuitive understanding of this system, but well, I try to express these features mathematically, and at the component level, at the control valve, well, there is a well, we have to consider the pressures and flow rate negation. And there is a control valve like that. There is a pressure in this side, and there is a pressure also in this side, and the pressure difference causes the flow of oil. And the relation can be described like that. And this R function, it's what I define. It's a sine square root. Okay, and this is a kind of typical, well, way of representing the flow rate. And check valves and relief valves, and they can be described like that. It's like exactly like diode in electric system. And we can describe the relation by using the normal cone functions, which is described, which can be defined like this. And yes, it means that the the flow is allowed to, well, it is allowed only in direction. So negative flow is not permitted. So well, the pressure difference and the flow rate can be connected by this kind of set value nonlinear function. And the relief valve is also it's similar. It's like that. So the P1, the difference between P1 and P2 is upper bounded by this, like this. And well, I applied this way of thinking, well, for the whole circuit, and well, we obtained 18 equations at, well, each valve and each junction of the circuit. And yes, some of them are equalities and some of them are, well, inclusions. And well, there are 19 variables, such as, well, the flow rate of each part and also pressure of each part. Yes, I guess so. And what we want to get is the relation between velocity and force at the actuator. So we have to eliminate all variables other than F and V, and I did it manually, and I finally ended up into this equation. And yes, this, well, function gamma, it is the set value function. It can, well, defined like this. And it looks complicated, but it gives us quite an, well, intuitive picture about how it works. And it is basically with a particular value of U, its graph becomes like that. And it's a connection of several curve segments, yeah, like this. And yes, and each segment has physical meaning. For example, in this section, the relief valve is open, and also, well, in this segment, it's an effect of, well, check valve in the circuit. And well, there are some segments. It depends depending on the condition or open closed states of or some valves. And yes, and the important thing is that they are the force is well such bounded, upper bounded and lower bounded, and there's some set valuedness, non-smoothness here. And this curve changes according to you. Well, like this. Well, and well, if we map this into the three-dimensional graph with B, velocity and force and the control of input U, well, it becomes like that. So there are some vertical parts, and it represents the set valuedness, meaning the non-smoothness. Okay, and okay, then now we got the set valued actuator, but well, set valuedness, meaning that the force can be any value between, well, some value to some value, but it sounds like that, well, the force is not determined. So the force is indeterminate. Yes, actually, when the actuator itself is alone, well, it's not connected to anything, then we cannot determine force. But when it is connected to something else, we can determine that. Well, for example, in this case, well, we assume that the mass is connected here, and there is external force G here, and then there is the equation of motion of this object, and this force is the actuator force. So yes, the actuator force comes from the actuator, non-smooth actuator, and so here we have V and V dot here. It means that there is differential algebraic constraint. Well, determining V, and once we determine V, we can determine X. So so it means that it doesn't mean indeterminate. It does not mean that the force is indeterminate. And a similar thing can be said about this situation where it is connected to spring and damper, and in such case, well, the spring damper force is here, and well, actually the force is determined here. So here we have also differential algebraic constraint with respect to E. So we can determine that. We can determine E, and also we can determine F. And so you may feel well, you may wonder if there is guarantee of uniqueness of existence, but it is relatively easy because the gamma function I showed you in previous slide, it's maximal monotone with the negative of B. So well, it's quite easy to prove that there is always a solution. And if we want to do simulation of this system, and we can discretize that. This equation of motion, it is discretized by backward Euler method, and it's increased discretization with the sampling time step size t, and we have this equation constraining the unknown f, and well, and it can be solved like that. And to do that, we have to define another function gamma eta, which is a bit slanted version of the function gamma, but it's single valued, and it can be defined uniquely. And by using that, we can describe the kind of discrete time solution, this algorithm to show compute to integrate that in discrete time. The same thing can be said about this system with spring, and yes, we end up in this algorithm, and we applied this one to develop a real-time simulator based on the second version, the connection with spring damper system, and now we are using that for preliminary checking of the controller. Okay, And this is the first topic. And the second topic is a model-based implementation of sliding mode controller, non-smooth controller to non-smooth actuator. And okay, now we have non-smooth actuator, and we have to control it. And specifically, we have to control the position of the actuator. And yes, we assume that it is connected to mass, and the position can be measured by position sensor. And we have to construct a controller to make the position follow the desired position PD. And well, no one has ever considered such non-smooth actuator. And well, it is not only for hydraulic actuators, but well, maybe there might be some other non-smooth actuator, but I'm not aware of other examples. Okay, so anyway, we need theoretical foundation to well develop this controller. And yes, so in such case, with the straightforward way is to manipulate the force that the actuator can produce. But and the reference the force, when it force can be commanded from a controller, then we can use some common position controllers. So let's say that we have some common position controller F hat and that produces F hat, and this reference force, if this reference force can be translated here, then we can control that. But there is something well different here, and we can put some well inverse function of gamma here. But well, we cannot guarantee if how we are not clear how F hat, F and F. We cannot guarantee that well they are equal to each other. But we have to remember that if this one well it is determined by the defined algebraic constraint in the plant, which means that the actuator force and this is the well equation of motion of the system and yes, if it's determined by this constraint, so we have to use this information to determine F. So the discrete time, and I actually in the previous slide I showed you the discrete time algorithm to compute this part, and we can put this here, and then well we can construct a controller like this, and this is well the kind of basic way of thinking to construct the model-based implementation of this system. But well here if well the force F with common controllers F can be any value, but this actuator it is saturated, it is bounded, so we cannot use some limited class of controllers. We can use what we can use is only limited class of controllers. So we constructed a sliding mode controller, which is basically it is the switching between the maximum force and the minimum force, and to constrain the system on the sliding surface in the state space. And so we put the sliding mode controller here, and it makes the actuator produce the maximum effort to achieve the sliding surface. And yes, it's and by discretizing that, we arrive in this controller and we apply that. And we yes, by discretization we obtain this algorithm. And yes, it works in a simple simulation, and it exponentially converges to the desired position, even when there is some unmodeled disturbance and unmodeled the unmodeled plant error. And how long do we have? Sorry. Okay. So yes, it's yes, it works in excavator. Apply that in excavator, but well, we needed some yes, we need some use some dead time compensation for this. And okay, sorry. Yes, I applied this one. The second way of thinking, well, spring and damper system, and yes, I did a similar thing, and yes, it works better than the first one. Okay, that's all. Thank you very much.